what is the probability of error? Half. And that d prime, you can see also from our expressions that say the responses are identical in the two neurons. And the two is always in the two non-neurons, the two conditions. The mu2 will be equal to mu1, d prime will be 0, and in that case, probability of error is 0, and then it's a non-monotonic, highly nonlinear function. When d prime is large compared to 1, the probability of error is extremely small. Okay, and then we got expressions for d prime in terms of for the optimal weights and for the d prime in that case. So the optimal weights for c minus 1 g. And there's a prefactor that you can choose as you wish. So maybe I will write like this. And the d prime square optimal, d prime without square. Optimal is g transpose c minus 1. So,
so the d prime square was equal to d prime.
What the question again? Why is that true?
D prime is equal to gt c minus 1g.
Because I just derived it. I took this expression and I.
No, but you said also the d prime not square is equal to.
No, it's without the square.
Yeah, but there is a square also.
So there is a square. So, thank you. You're right. There is a square. Let me just go through my notes and make sure that I did not put it in. Okay. I think it's with the square. I just wrote to you what is d prime square, so this needs to be checked, but I think that this is correct. I think it's with the square. Okay, so so this is general. This is for any choice of the G's and any choice of the covariance matrix. And I will do in a moment some examples, but I just want before that to look at these expressions and see that they make sense. So there are a few things to check which are kind of trivial, and it's always good to check things like that. So if G is 0, G0 means that the response to the two neurons, to the two conditions, θ1 and θ2 are the same, right? Or in other words, if Fi plus minus Fi minus is 0, then the vector G is just a vector zeros, and then d prime is 0, and we cannot discriminate. We have a probability of error of half. So the larger, in the basic sense, the larger the difference between the responses to the two conditions, the better the discriminability. And C is a covariance matrix of the noise. So just qualitatively speaking, if there's lots of, the noise has large variance, then C, the matrix C, not the inverse of the matrix, the matrix C has large elements, the inverse is small. So lots of noise makes this thing smaller, which also makes sense. Lots of noise, which decreases tends to decrease the discriminability. Or in other words, if we would multiply the covariance matrix by a factor, not changing its structure, like multiplying it by a factor, then the discriminability will always decrease. Okay, so now I want to do some examples. Consider some examples. And the examples that I will do are motivated by the simple examples that I discussed with you in the beginning of our discussion on correlation. So I discussed an imaginary situation with two neurons, and now we'll do it with n, but still, I hope you will be able to see the similarities. So the first example that I want to discuss is n identical neurons, and which are also uncorrelated. And I want to see that what we get from this expression makes sense. So GI, which is Fi plus minus Fi minus, we assume that it's the same for all the neurons. The neurons are identical to each other, independent of I. And the fact, if the neurons are uncorrelated, it means that the covariance matrix is diagonal. So let's denote it by A times the unity matrix, and I'm assuming that it's the same value on the diagonal because I'm assuming that all the neurons are equivalent to each other. Okay, so what does this formula tell us? What would the optimal weights look like?
You look like G multiplied by A.
Okay, A was.
A by the power of minus 1.
So remember that we discussed before that actually the magnitude of the weights doesn't matter anyway. So what can we say about the optimal weights?
Proportional to G.
Okay, which
Uniform.
uniform. The crucial thing is that the optimal weights are independent of the index I. They're the same for all the neurons. If we take this matrix, its inverse is also proportional to the unity matrix. We multiply it by G, which is a vector which has the same entry everywhere. We get again a vector which has the same entry everywhere. What is the entry? Doesn't matter because we can, from the start, the magnitude of W doesn't matter. So we can just say that the optimal weights are some number, W. You can choose it as we wish, it doesn't matter. What can we say about the optimal D prime? Okay, so now we need to take this vector, which is a vector of G's in every entry, and make a sandwich with this vector around this matrix. So we'll have the prefactor within this vector, which is G, the value within this vector will appear twice, both here and here. And from the matrix C, minus 1 will get 1 over A. The inverse of this matrix is just 1 over A in every element. And then all this is multiplied by the vector of 1, 1, 1, 1, 1 times a matrix that has 1s in the diagonal times this vector. So what does that give us? What does that give us? This matrix times this vector, this is unity matrix, so it's just this vector. And then when you take this vector multiplied by itself, what do we get?
The number of neurons.
Number of neurons, n. So we get n G squared over A. So this is the optimal discriminability. So you see that the larger the number of neurons, the better, right? The larger the number of neurons, the better. The larger the difference between the response of each neuron in the two conditions, the better. The larger the variance of the noise, the worst. More noise, detrimental. But you also see what happens here. We take our neurons. Our discriminator is just summing up their activity. So it's clear why we get a discriminability that scales like n. The sum of the activity of all these neurons is also normally distributed. It has a mean which is n times the mean of a single neuron, and it has a variance which is n times the variance of a single neuron. So the standard deviation is square root of n times the standard deviation of a single neuron. So when you have more neurons, the ratio between the standard deviation and the mean of the whole, and the sum of all the whole response it becomes smaller. So it's less noise. We average over the noise. Let's check another trivial case, which is n identical correlate. Well, actually, I will not do it trivial. I will do it a bit. Right, so I will want to do n identical and correlated neurons. but I won't do fully correlated. So let me explain what I mean by that. So identical, first of all, means that Gi is still going to be independent of I. And the correlation matrix that I'm going to assume because I'm assuming that all the neurons are equivalent to each other, it will only depend on whether the index I is equal to J, which is the covariance, the variance of a single neuron, versus the covariance between two different neurons. So I want to write a matrix here that has a certain value in the diagonal and some other value elsewhere. So one way to write it. So maybe first I will write explicitly what I mean. So as in this case, I will put an A here and put ones over here on the diagonal. So if now I would put zeros everywhere elsewhere, this will be the case that we already discussed. But now I will imagine that there is some other value in all the elements of the covariance matrix which are not the diagonal. So,
the same?
Yes, the same. And the same because if I'm assuming that all the neurons are equivalent to each other, it means that it cannot depend on the index of the neurons. So the variance of a single neuron is A, and the covariance between two neurons is alpha times A. Let me write this matrix in mathematical notation. So it's, if I is equal to J, we have A. And if I is different from J, I want to get alpha A. So I will add here alpha times 1 minus delta J. So this is this matrix. Now, before we continue to calculate the optimal weights and the optimal discriminability, I want to discuss a bit what this matrix, what values alpha can take. So first of all, if alpha is equal to 0, we're back in the uncorrelated case. Now, what is alpha? What happens if alpha approaches 1? Or let me write, if alpha is equal to 1, what happens then?
All neurons are fully correlated.
Yeah, right. Then the correlation between any two neurons is the same as the covariance. So this is a fully correlated case, and in fact, the only way this could happen is if the responses are identical. Okay? This means that the neurons that the responses of all the neurons are identical on a trial by trial basis. Turns out that alpha cannot be larger than 1. What was the question?
Is it an assumption or it comes from
No, it turns out. So how could we hope to, why can I say something like this? Alpha, how can I show that there are some restrictions on alpha?
Because neuron A equals alpha neuron B, and neuron B equals alpha
Yeah.
neuron A.
Yeah, so it doesn't make, okay, but, well, it's not equal. It's, this is the structure of the covariance matrix. Right?
It's still
Okay, so
not fit together.
So the way to ask really what values of alpha are possible is to remember that this matrix has a property that it always has to obey, and this is a positive definite matrix. Okay, covariance matrix is always a positive definite matrix. No matter what distribution you choose for the elements, it always has this property, and meaning that, for example, all the eigenvalues of this matrix must be non-negative. And so you can show that if alpha is larger than 1, this matrix has negative eigenvalues, and there is no distribution, no way to realize such a matrix as a covariance matrix.
This is true for covariance matrix in general?
Yes, any covariance matrix is positive definite.
No, I mean,
Yes, any covariance matrix is positive.
talk about the restriction on alpha, but this is just a special case because everything.
Well,
as we
the
said,
reason that any covariance matrix is positive definite is that if you have some vector u which has some distribution, okay, any distribution, and you want to calculate the mean of u, some linear, and you want to take some, and so suppose that u has any distribution, not just Gaussian, not just normal, any distribution with the covariance matrix C, and you want to take some vector, some linear combinations of the elements of u. Something like, so let's choose some vector v transpose and multiply it by u. And now you want to ask what is the variance of this variable. You can prove that the variance of this variable is the sandwiching is v transpose c minus 1 c v. And the variance is always positive. So that means that if a matrix that has the property that for any choice of v, this quantity is always positive, is positive definite. So this is a way, I'm not doing it in detail, this is a way to prove that any covariance matrix has to be positive definite, or non-negative definite, but semi-positive definite.
but I asked about the restrictions on alpha,
Yes?
and you said that alpha cannot be larger than 1, right?
Yeah.
So is it just for this form for covariance matrix that all elements besides the diagonal are the same, or it's a general effect about
Well, if I didn't,
Yeah.
the definition of alpha is through this definition of the matrix. So, I mean, any covariance matrix has to be positive definite. If I choose if I want to generate a covariance matrix that has this structure, then if I cannot choose alpha to be larger than 1 because then it will be not positive definite. And I want to also highlight what's the problem with this. We wrote explicitly the Gaussian distribution, right? It was 1 over z exponent of r minus mu minus f1, or if I call it f minus, or f c minus 1 r minus f. What's the problem with this? If I could choose, it seems like I can choose a matrix C to be whatever I want. But if I choose the matrix C to be such that it's not positive definite, this is not normalizable. That's a problem. It's like having in the case, let's just imagine the one-dimensional case. In the one-dimensional case, not this example, it will be like this matrix would be positive definite if C is a number, it's a variance, and it has to be positive. If that number is negative, I'm trying to normalize, there's a minus half here. If I have something that looks like x of r squared divided by some positive number, because there is a minus and this is negative. So I have something which is not normalizable. It's a distribution which is not normalizable. So we can define a Gaussian multidimensional variable only if the covariance matrix that we try to put in it is positive definite. Otherwise, there are directions in which the Gaussian diverges instead of going to 0. Okay, so going back to this. Now we have a parameter that we can tune, and as we tune this parameter, we go from, in one case, when alpha is equal to 0 to the completely uncorrelated case, up to the fully correlated case. And we have the machinery to calculate what are the optimal weights and what is the discriminability. So let's plug this in. Okay, in order to do that, we need to invert this matrix, right? So the question is, how does the inverse of this matrix look like?
It's
easy when it's equal to 0.
Yeah. But just this matrix has symmetries in it, that it has a certain value on the diagonal and some other value anywhere else, which means that any two neurons are equivalent to each other. So what can we use that? How can we use that to find the inverse?
It will be of the same form.
Yeah, exactly. So the inverse matrix, so if this is C, I claim that without doing any work, I know that I could write the inverse of C in the form B, 1, beta, beta, okay, something like this. Because every two neurons are equivalent to each other, so there's no reason that the element of the inverse between some particular pair will be different from the element of the inverse for some other pair. So this I know without doing any work. Now we need to multiply these two matrices together and require that we get the unity matrix. And in this way we can find what is this B and what is beta. Okay, so I will not do that explicitly, I will just write the answer. B is equal to 1 over A times n alpha plus 1 minus 2 alpha divided by n alpha plus 1 minus alpha. There's a risk here that alpha and 2 in my handwriting can be similar. So if you're not sure, ask me. 1 minus alpha. What can I do? That's what it is. It's ugly, but that's what it is. And B, and beta is equal to minus alpha divided by n alpha plus 1 minus 2 alpha. Okay. What can we say about the optimal weights? So G is a vector which has the same entry everywhere. Yeah, they're also the same because there's nothing. If we multiply this line by a vector that has the same elements everywhere, and this line, we'll get the same thing, right? So the weights are still independent of I. And it makes sense. The neurons, there is nothing that differentiates the neurons from each other, so there's no reason we would choose different weights for different neurons. Okay. So this result, it's nice to see that it works out this way, but we could have guessed it without doing any calculation. And the key now is to calculate the optimal, the optimal discriminability. So we will have G squared times a vector of 1 multiplied by C minus 1 times a vector of 1. Okay, so what is that? What actually do you get when you multiply, when you sandwich a matrix between these two vectors, this vector on both sides?
Sum of all elements.
You get the sum of all the elements of the matrix. So we have two types of elements in this matrix. We have the diagonal elements and we have the non-diagonal elements. So we will get G squared times n times B, these are the diagonal elements, plus n times n minus 1 divided by 2, which is the number of non-diagonal elements, multiplied by B times beta. Right? Okay, why did I divide by 2? There is no division by 2. It's n times n minus 1. That's the number of non-diagonal elements. It's n squared minus n. You need to count both sides of the diagonal. Okay. So I can write this also as G squared everywhere here there is an n, so I can take one n out, and there's a b everywhere. So g squared nb times 1 plus n minus 1 times beta. And now we need to plug in the expressions that we have for b and for beta. Unfortunately, this looks like a big mess, but when you do everything, collect terms, you get something which is less of a mess than what you would expect. So the expression that we get is g squared over a times n divided by n minus 1 alpha plus 1. And now I want to look at this expression and see whether it makes sense. So, when alpha is equal to 0, that's the uncorrelated case. What do we get? G squared times n divided by a. That's our previous example. Right? When alpha is equal to 1, that's the fully correlated case. Then I have here n minus 1 plus 1. So n and n cancel, and I just get g squared over a. Does this make sense?
Like if we had 1 neuron.
Yeah, if I have n neurons that each time I observe them, they give me the same answer, it's just like having one. Right? And if alpha, what is more interesting a bit is to look at alpha which is between 0 and 1. And then we have a function. Then we have a function of n. Right? And initially, when when n is very small, because we have here a 1, so initially we can forget about, initially usually suppose that alpha is small. So initially, when n is small, this term is negligible compared to this one, and you see that the behavior is like the uncorrelated case when I start to add more neurons. But at some point, this term becomes comparable to 1, and eventually it wins over. And when it wins over, we have here something which is proportional to n, so we will saturate. So this function, if I would plot it, p prime, will start growing as in the uncorrelated case, and then at some point it will saturate. And we can write down what is the behavior for large n. So d prime square, when n goes to infinity, we can forget about this, we can forget about this, so we have just 1 over alpha. So we have g squared divided by a alpha. So remember, alpha is smaller than 1. So we get a better discriminability than for a single neuron. But we saturate. At some point, when we add more and more neurons, the fact that they have some partial correlations between them mean that at some point we don't gain any more by adding more neurons. Okay? All right. Let's do another example, which will be illuminating. So we have now, let's imagine that we have 2 populations of neurons. opposing responses. So I imagine that one group of neurons increases its responds more to theta 2 than to theta 1, and the other one responds more to theta 1 than to theta 2. So my model would be that GI, which remember is Fi plus minus Fi minus, is some positive number or some number for the first set of, for half of the neurons. So I assume the number of neurons is even, and it's opposite for all the other ones. Okay? And for Cij, I will still assume the structure that we discussed in the previous example. So the neurons are all, the noise is partially correlated, and it does not care about the identity of the neurons. So it's A delta Ij plus alpha 1 minus delta Ij. So C minus 1 is still this. Nothing changed in C compared to the previous example. So with these particular values of B and beta, I will erase it just to continue, but we will use these values. Okay, so still C minus 1 is B times 1 beta. Okay. Okay, what can we say about the optimal weights? What is the structure now of the optimal weights? So remember, to calculate the optimal weights, you need to take this vector and this matrix and multiply by this vector. What will we get?
The G of that segment. The GI.
Not exactly, no. Remember that actually the value of the weights doesn't matter. It's just the structure, the direction. What kind of vector? So in the previous examples, we got a vector that has the same entry in all positions, right? What changes now? So I have some matrix with this structure, and I multiply it by vector.
Normalize once and
Vector that
once.
has a G times 1, 1, 1 up to this point, and then minus 1, minus 1, minus 1, minus 1 up to this point.
It's 0?
No, it would be 0 if beta was 1. But beta is not 1.
It will be the vectors of the ones and the minus ones.
Yeah. So that's what happens.
Yeah, it's the same as G, but normalizing.
This is what you meant. This is what you meant when you said G, that it's a vector G, and you were correct. So, so actually, you see that the only thing that matters is whether the 1. So we multiply a line of this matrix by this vector. The only thing that matters is whether the 1 falls in this part or in this part. And you can convince yourself that the answer will change signs in these two cases. So the optimal weights have the structure W sub W. Remember, we can choose it as we wish. Times 1, 1, 1, minus 1, minus 1, minus 1, minus 1. Does this make sense? What does this discriminator do? discriminator takes these weights and multiplies them by the neural responses, right? What does it do?
Sum one population.
Yeah, it sums the population that increases its response and subtracts the response of all the neurons from the population that decreases its response. It makes a lot of sense, this is what it's doing. What about the discriminability? So for the discriminability, we need to take this vector, sandwich it around c minus 1. So we have g squared times 1, 1, 1, 1, minus 1, minus 1, minus 1. C minus 1, 1, 1, 1, 1, minus 1. Something like this. And well, this is the matrix C minus 1. So in order to do this, it's convenient to think about this matrix C minus 1 is composed of 4 smaller matrices. One is a matrix that has 1s on the diagonals here and beta here. This one also has exactly the same structure. So these two smaller matrices exactly have the same structure that C minus 1 had for the full N. And then here we have matrices that just have betas over everywhere. Right? And so when we take this sandwich of this vector around C minus 1, we'll get the contribution from these terms, which is a sandwich of these terms around this matrix. We'll get another one from this and this around this matrix, but it will be the same, because there's a minus sign here and a minus sign here. And then we'll get a sandwich of this vector with plus 1s and minus 1s around this matrix. And we'll get it again from this and this around this matrix. So let's do it explicitly. So I will write down a 2 because everything will have twice. We'll have this sandwich around this matrix, and it appears twice again from this part. So let's write that part down. So this part actually has the same structure as what we did in the previous example, except that n is replaced by n over 2. So we get 2g squared b times n over 2 plus n over 2 times n over 2 minus 1 beta. It's exactly what we wrote, again, in the previous example, except that I replaced n by n over 2. And it appears twice. And then we have these terms where we have 1 multiplied by this matrix times a vector of minus 1. What will that give us? So I claim that it's, because there's here a plus and here a minus, there will be a minus sign, and then just the sum of all the elements in this matrix. So we have plus 2, 2 because we have it twice, times minus 1, times n over 2 squared, that's the size of the matrix, times beta, times b times beta. There was a b here in front of all of this, right? Times b times beta. Okay, this looks even worse. Now we need to plug in the expressions for b and for beta. And so this looks even worse than what we had in the previous example. But actually, when you do all the math, you get an even more simple answer. So when you plug it in, when all the dust settles, you get g squared n divided by 1 minus alpha. So this result is remarkably different from the result that we got previously. Previously, when alpha and I think there's an A missing here.
Mm-hmm.
So I will just put it like this. Because it's missing in my notes, but it has to be here. Okay, so one case which is similar is the case where the neurons are completely uncorrelated. Alpha is equal 0, so you can see that we get exactly the same result as in this case. But once we put in some correlations, you see that in this case, when the responses of the neurons were the same, the discriminability is saturated when n went to infinity. Now it does not saturate anymore. Now if the neurons have different responses, even if they have very little correlation, it doesn't matter how much correlation they have, or a very large correlation, doesn't matter. The discriminability improves as we add more and more neurons. Okay? And it's kind of intuitively should be clear why. We're now removing by the ability, because the neurons have different responses, we can take the difference between the response from this population and this population, which in fact is what we're doing, right? And the correlated part of the response completely goes away. We remain only with the uncorrelated part of the response. Moreover, now in contrast to this case, when alpha is larger, we're doing better. Not only are we doing better, when alpha approaches 1, the discriminability diverges. And as a particular case, if n is equal to 2, we discussed this last time. If we have two neurons that have exactly the same response, noise part of the response, we can take their difference, with still the difference, because the g's for one neuron is positive, for the second neuron it's negative. The difference is informative about theta, and if the noise part is identical in the two neurons, when we take the difference, we eliminate the noise completely. And so this explains why when alpha goes to 1, we get infinite discriminability. We can actually remove the noise altogether.
But this is only an average, no? If you just take one neuron and...
No, it's not an average. In the limit, it's an important question. In the limit where alpha is 1, the noise is fully correlated, meaning that on trial-by-trial case, the noise is the same in the different neurons. And so if we calculate this times the responses, when alpha becomes 1, the noise in all these neurons is the same as the noise in all these neurons, and we just subtract, we eliminate the noise completely. And that's the key why when alpha goes to 1, in this case, discriminability diverges. Okay, I think we will stop here. There is a bit more that I want to say about these examples, and then we will look at another example. We'll do this on Thursday.
לא, כי זה מה שנותן את הכוח. אם הן שונות, אז הן לא אמורות, למה איפה באה הקורלציה הזאת? זה לא תמיד באותו... כן, אבל זה מוזר. לא, זה לא שאלה שונות באותו...